now we are going to start with module 2. So here if you see, first we are starting our module 2 by discussing what is a Euler graph. Okay, what is Euler graph? That is what we are going to start our discussion on. Fine. So a graph theory tracks back to 1736 with the Euler paper, the 7 bridges of Königsberg. We know in Königsberg, which we have already learned in module 1, whether it is possible for us to cover all that bridges like one time only. If I am able, I have to cross every bridge one time and cover all the island, right? So is that possible or not? That is where our question comes. Okay, so Euler graph means there exists a closed arc in a graph G that contains all the edges of G exactly once. Then such graph is called as Euler line, and the graph G is called as Euler graph. That means if there is a closed arc, we are considering about a closed arc. Okay, in that closed arc for a graph, we are covering all the edges exactly one time. Such a arc where we are covering all these edges exactly one is called as such arc is known as Euler line, and such graph and the graph G here is known as the Euler graph. That is what Euler graph's definition is. So in a Euler graph, it's like a closed arc actually. Okay, it is a closed arc where we are covering all the edges in that graph exactly one time only. We are covering all the edges in that graph. Okay, so such a closed arc is known as a Euler line, and such a graph is known as Euler graph. Understood? Since a Euler line covers every edges and a Euler graph is always connected, so now we can say what we have talked about Euler line. We have understood that Euler line means what? It is covering all the edges exactly once. Since it is covering all these edges exactly once, that means it is what? A Euler graph is a connected graph. So we assume Euler graph has no isolated vertex, so an Euler graph is always connected, and we are assuming that sometimes there can be isolated vertex, right? So there would be no isolated vertex in Euler graph. That is what we are basically assuming. So we are assuming that there is no isolated vertex in the Euler graph. So therefore Euler graph is always a connected graph. So that is what you have to understand. Euler graph is always a connected graph and there is no isolated vertex. Understood? So this is our main thinking. It is a connected graph. This is the same thing we are saying. So Euler graph is a graph in which you can start at a point and travel through every edges exactly once and return to the starting point. I hope you have understood. We are starting at one exactly like you are starting at a particular point and you are traveling all the edges exactly once. You are traveling all that edges, right? Exactly once only you are traveling all that edges, and you are returning to the starting point. This is called as Euler graph. So if there exists a closed arc in a graph G that contains all the edges of G exactly once, then so there is a closed arc that in a graph G which contains all the edges of G exactly once means such a arc is known as Euler line, and such a graph is known as Euler graph. So a closed arc, a path that starts and ends at the same vertex. Euler line, the route that contains every edge exactly once. Euler graph, a graph where such route like Euler line route is possible or is existing. Fine. In Königsberg's problem, we have seen that such a path was not able to get. We were not able to get such a path. That was the main thing in Königsberg's problem. So that the graph was not a Euler graph in Königsberg, right? That was the main thing that we have understood there. Fine. Now let's see here. A Euler graph is always connected. There is no isolated or disconnected vertex. So we have understood that a Euler graph is what? It is always connected. They are not isolated or disconnected. The classic condition, a graph is Eulerian if and only if every vertex has even degree. Now another important thing that is we will prove this theorem also. If a graph is Euler graph only, we can say that when all the vertex in that graph is even degree. So we have to prove this theorem. If there is a connected graph G and it is said that connected graph G is a Euler graph, the corrected graph G is a Euler graph if and only if every vertices of that G has an even degree. So this is a theorem, and this is one of the most important theorem that we are going to now prove. Understood? So a graph G is considered to be a Euler graph if and only if that graph has even degree. If all the vertices of this graph is even degree. So what does that mean? First, let's understand what does that theorem means. So Euler line or Euler circuit means a arc that starts and ends at the same vertex. That means it is using every edge exactly once. So a Euler graph means a graph that contains such this arc. If a graph contains such a arc, then it is called as Euler graph. This much we know. So we are going to prove it in two parts. That is, part 1 means if G is Euler, then we have to prove that all vertices even degree. Then the second part is this. The second part is the this is the second part, right? Yes, this is the second part. In the second part is the opposite condition. If all the vertices are even degree, then we have to prove that the graph is a Euler. So that is a second part, right? So this would be my second path. So we have to prove this in two paths. So first part 1 is that if graph is a Euler graph, then we have to say that all vertices are even. So if you can travel every edge exactly once, and Euler graph means what, you are traveling every edge exactly once and returning to that same point. Something must be true for each vertex if it has to do this condition. So how you would write it in the exam is that you have a G graph which is a Euler graph. So if that graph has a Euler circuit, means every time you reach a vertex, like if I'm saying that, I'm assuming that this graph, there is a graph G which is a Euler graph, so there would be a Euler circuit in it. So every time you reach a vertex, you enter through one edge and you leave through another edge, right? That means if it has a Euler line in it, you have a vertex V1. So I will enter to this vertex through one edge and I will leave this vertex through another edge, right? There should be an entering and leaving there. All the edges would come in pairs, right? All the edges are coming in pair. One which is entering a vertex and one which is leaving a vertex. Because then only we can say it's a Euler graph, because every vertex has to be covered, has to be gone exactly once. So that means every edge exactly once only, one time only it is entering. So one time one vertex would enter, one edge would enter this vertex and leave this vertex. So all the time we have to say that the edges are used in pairs, one for entering and one for exiting. So this is true for all the intermediate vertex and even the starting vertex, because since it is a closed arc, you know, Euler graph has a Euler circuit which is a closed arc. Since it is a closed arc, if you consider the starting vertex also, you are from the last vertex, you will enter to the starting vertex and you can leave from the starting vertex to the other vertex, right? Since it is a closed arc. So even in the starting vertex, the edges are coming in pair, one for entering and one for exit. So that means degree of every vertex would be what? Since edges are coming are pair, for each vertex there are two edges which is touching that vertex. So the degree of every vertex here would be what? Even, because the edges are coming in here pair. So this is what we can say. This is how we will prove the first part. If a graph is a Euler graph, all the vertices have an even degree. This is how you prove the first path. Okay, so I hope you have understood how we are proving the first path. So here in the first path, how we are going to write it in the exam, we are going to first say that we are going to consider a graph G which is a Euler graph. If this graph has so we can say that it has a Euler circuit every time you reach a vertex. That means, how can we say this graph has, if this graph has a Euler circuit, every time when you reach a vertex, there would be every time there would be one edge that will enter to this vertex and one edge that will leave that vertex. So that means the edges are coming in pair, one for entering and one for exiting. This is the case in all the intermediate vertices. So here what happened is that all the intermediate vertices also, even the starting vertex also, because Euler circuit is a closed arc. So therefore we can say that degree of all the vertices is even here. So therefore, hence we prove the first part. If G is Euler, then all vertices has even degree. Now for part 2, we are considering that our all the vertices are even degree. Then we have to prove that that graph is a Euler graph. Okay. So step 1 is we are going to start walking here. Okay. We'll pick any vertex V and start moving along the edges, and we don't need to repeat that edges. That is the main rule of the walking. You're going to start walking here. You're going to pick any edge vertex in the graph, and you're going to start walking through its edges. And the rule is that the edges should not repeat. Okay. Can you get stuck? Whether you get stuck while you're walking, let's see. Let's think. When you enter a vertex, you use one edge. To continue, you must leave using another edge. So edges are used in pair, right? That we know. Since every vertex has an even degree, total edges at that vertex is even. Since every vertex is an even degree, the total edges in that vertex would be even. So used edges also form the pair. So you will always have one unused edge to leave. So that you have to understand that the total edges of that vertex would be even. So you will always have one unused edge to leave there. So you will not get stuck anywhere while you're walking. So you're going to start walking. You will start from one vertex and you will walk through each of the edges from there. The rule is that the edges would not repeat. So the main thing is that whether you will get stuck. So if you see here, when you think whether you get stuck, we know there is one edge for entering and one edge for leaving, because the edges are coming in pair. We have learned if it is even degree, each of these vertex has even degree of edges. The total edges at that one particular vertex would be even. So there would be always one unused edge that you can leave. So you are not going to get stuck anywhere. Now where you are going to stop? When you are going to stop is that when you have reached the starting vertex again, you form a closed cycle. You formed a closed walk. You form a cycle. Let's call it as H. So you will stop when you are reaching to the starting point again. So you completed one cycle. Now, are you sure that this H contains all the edges? Let's say sometimes this edge does not contains all the edges. Some edges are being left out in that. So what you're going to do is that remove the edge which is already there in H. Then you will get, that means a graph means that it's not like this graph is completely a closed walk. No. A graph would have this Euler graph. That means a graph G would have Euler circuit actually. Not wholly it is considered to be a closed walk. Okay. So there would be some edge that may be unused here. So what you're going to do is that you're going to remove the edges which is there in this H closed walk, that is in the H closed walk, and then you will get a subgraph G dash. And in G dash also all the vertices are even. So G dash is still connected to original path somewhere. So pick a vertex from H that is still has an unused edge and start another walk H dash. Now what you're going to do is that you have this H and H dash would be actually H dash is going to, you are going to start another walk H dash. Okay. So there are still some unused edges from H, and still has, you're going to pick a vertex from H. Okay, from H, because we wanted a connected graph, right? So from H you will pick a vertex which has a unused edge in H. From H you are picking a vertex which has unused edge. So that we will start from that another walk. So you won't get stuck because you will find another closed walk there. Okay, you are not getting stuck there again. Now you're going to combine the walk. You have first walk H and another walk H dash. Now you're going to insert this H dash into H. Like first our path was A, B, C, D, A. We reach A again. But from B there is E, F. There is E, F which is unused edges are there. So that is the thing you have to understand here. From this example you will get very clearly. First I am starting from A, then I go to B, C, D and A. So one cycle is done. But actually if you see, the B, E, E, F and FB edges are not used yet. So that means I am going to pick, this is my H. This is my H. From this edge, I'm going to pick that vertex, that is B, which has unused edges. So from B, there is some unused edges, that is B, E, F, B. That is, this is the unused edge. From there, I will start another walk. This is, let's say, H dash. Now I'm going to insert this H dash into H. So what I will get, this combined, you can see here in the down, there is a combined graph, right? This combined graph I will get when I did that. So I will get a combined graph. So from this, this combined graph is starting and ending at the same place, and also there is a closed path in it. So that means here, if you see, if there is again remaining edges, you have to repeat the same process. Final result is what? You get a one big closed path which is covering all these edges exactly once. This is called as the Euler circuit. So in this way, the part 2 is proved. So I will just say this theorem once again. So the first theorem, first you have to say what is Euler graph and what is Euler line and what is Euler graph. Then we are first proving if G is a Euler graph, then we have to prove that all vertices has even degree. So you are saying that if it has to start at one point and starting and ending vertex is same, then it has to cover every edge. Then that means this vertex would have something, some condition should be true in that vertex, right? So if it is a Euler circuit, means we are covering every edge exactly once. So each vertex, if you consider, there is one which is starting vertex, that is one which is entering, and one which is leaving is there. So the edges are coming in pair. So each of these vertex has edges which are coming in pair. This is true for all the intermediate vertex and the starting vertex, because it is a closed one. This is how we are saying. So that means the degree of all of these vertex would be what? Even. Hence the part 1 would be proved. Now for talking about part 2, that is, if all the vertices are even, then I have to prove that it's a Euler graph. So for that, what I will say that I'm going to start walking. Okay, I'm going to pick any one vertex and start going through each of the edge. The rule is that we should not use repeated edge. Okay, now we have to think whether you will get stuck or not. Since we know one vertex, one edge is there to enter the vertex and other is there to leave. So that means edges are coming in pair. So we have already said that we are using even degree here. Even degree of vertices. Even degree. Every vertex has even degree. That is what the condition is. There is even. All the vertices are even degree. So if all the vertices are even degree, that means that total edges that would be coming to this or leaving this vertex, total edges at that particular vertex would be even. So if I am entering a vertex, then I would have a unused another edge to leave, because the edges are coming in pair, because we have even degree of vertices. So we are not going to get stuck anywhere. So what happened when you are going to stop when you reach the same vertex where you have started? So you get a cycle edge. Now whether edge covers all the edges, maybe not, maybe yes. If it doesn't cover, we are going to consider what you're going to consider that you're going to remove all the edges from edge, and you're having another graph G dash, that is a subgraph of G, which would also contain all the vertices even degree. So from that subgraph, we are going to choose that vertex which has unused edge, and we are going to start walking again. You will not get stuck again. You get a closed path. You will actually reach another. You are going to stop it when you get the same path where you have started it. Understood? So that means now you get another walk. Now we are going to insert this. Let's say the new walk you got is H dash. Now we are going to insert this H dash into H. That is what the next thing, right? We have inserted this H dash into H. So you get a complete Euler circuit here, complete closed walk. If there is more remaining thing, you have to repeat it again and again. So this is the final theorem proof. I hope you have understood it. Okay, thank you.